You look this way. Okay. Heck, guys, stop talking. Thank you. Does this look familiar to you? Something like a ring-like structure like this. You've probably seen this when you were in middle school. Okay. This is going to be what we used to call the Bohr. Well, the Bohr model is only true for hydrogen. People used to just say everything was the Bohr model because it was really easy to say, oh, the first energy level can hold 2 electrons. The second energy level can hold 8 electrons. The third energy level can hold 18 electrons. And so it used to be really easy to say that. But this whole energy level business, it's only true for Bohr in this concentric circle kind of way. Now we know they have these funny looking shapes, right? So the reason I'm showing you this is because you can see that, we can track hydrogen has a first energy level has 1 electron. And then over here, helium in the second energy level, make this a bit bigger here, it's got 2 electrons because it's number 2, right? Keep going. Lithium's got 3 electrons, but you see how they went from the first energy level with 2 electrons to the next one having 1 electron? So we've probably seen this built up like this before. But these are lies for upper level chemistry. So we can use them as like a basis of understanding the basics, but actually to get into the real details, things start to look more like, this picture's horrible, it's really hard to see this. Things start to look more like our balloons that we were talking about yesterday. We would have like a spherical shape for the s orbital, and then on top of that, we can draw another s orbital, which is kind of like what it's showing you. But then on top of that, we would draw a p orbital. How many p orbitals did I have yesterday? 3. Remember, one was in the x-axis, or this is the y-axis. One was in the x-axis, and then one was in the z-axis. We're supposed to be going into the board and out of the board. So you can see it starts to get more complex because you're building on top of each other, all of these balloons. So these are going to allow for us to precisely determine approximately where electrons exist. Because some electrons are going to live in the inside, some are going to live out here in the second S sphere that I drew, some are going to live out here, and all of these little balloons. So it starts to give you like more of an address or the location where the electrons are. So the words that we talked about yesterday, principal quantum number, in the N number, the energy level, or SPDF, things like that are going to come back into play. Okay, so let's talk about that now. There are a couple people who are key players. Key players are these 3 people here, and how we determine where electrons existed around the nucleus. So these guys you'll see on problem set 5 and in your book, and we talked a little bit about them already. So electron configurations, it just means how the electrons are configured, how they're laid out amongst the electron cloud. So these guys came to the conclusion that electrons, they follow some rules. We may not be able to determine exactly where they are and exactly the speed they're traveling, but they do follow these rules. So I remember them in a really, really silly way. Mr. Offball came up with this principle that whenever electrons are filling an atom, they always start out awfully low. Okay, so Offball, awfully low. This is my little silly mnemonic, so I remember. Offball says the lowest energy level is filled first. Like, we're going to start from the bottom, and then we're going to build up from that. We're not going to start at energy level 7 and throw an electron in there because that doesn't make any sense. So generally that means you start off at n equals 1, you put some electrons in there. And I'm going to kind of go with the Bohr picture just because it's more familiar. Then we're going to go out here to n equals 2. We're going to throw some more electrons in here. It's up to 8 in this one, by the way. 1, 2, 3, 4, 5, 6, 7, 8. So that's what I mean. I'm saying start from the middle, or the lowest energy level, and then build outward. That makes sense, though, right? Okay. Just like, how you would do anything. So after that, Mr. Pauly came in and said, okay, there's also this propulsion issue we have to deal with, because when electrons get really close to each other, they start to do what? They get really just unstable and they start to repel each other, right? So the whole repel issue needs to be addressed. So the way he said it becomes addressed is we can't put too many electrons in one spot. We're only allowed to put 2 electrons in one orbital. One orbital being in the s orbital, you're only allowed to put 2 electrons. And remember yesterday I drew them as arrows? One spins up and one spins down. In the p orbitals, the one that looks like that, I can actually put them here and here, because that's one p orbital. And the other p orbital, I can put them here and here. And then the other p orbital, I can put it here and here. So I'm following the Pauli exclusion principle by only putting 2 electrons in each orbital. It's just after that it becomes too crowded and electrons start to repel each other and becomes very unstable. And then we come to Hund. So off-ball, awfully low, starts at the lowest energy level. Pauli pairs, that's how I remember that. Electrons occur in pairs, 2 at a time, that's it. And then Hund's ones rule. Hund's ones rule. I try to come up with little rhymes here. So Hund was like, oh man, look, if we only have 2 electrons or five electrons, how do they fill up in these orbitals? Do they double up or do they do singles at a time? Well, think about it. If you got 2 negatives and you have a choice to put 1 in this orbital and 1 in this orbital, or both of them in the same orbital, what is the better choice? So if I said if I have two orbitals to work with, I put 1 here and 1 here, 2 electrons, those negatives are separated, right? That's happy, that's good. You put them both in the same orbital, they start to repel each other. So if by chance you have the opportunity, you want to do 1 electron per orbital first, and then if you have to go back and fill up, you can. But what I'm saying is for this one, the S one, you have to fill the S orbital first. It gets 2 electrons automatically. You have no choices. But for the P orbitals, they all occur at the exact same time. You've got 1 up here, you've got 1 sideways, and you have 1 out of the board and in the board, right? So let's say the next set of electrons I have 3 more electrons. I'm not going to go 1, 2, and then 3. I'm going to go 1 at a time. 1 in that orbital, 1 in this orbital, and then 1 in this orbital. Only because that allows for the repulsion of these 3 electrons to be very limited, because if I put this one in here, we've got some repulsion happening. And remember, those arrows represent electrons. Okay, does that make sense? The rules. 3 people. Off-ball, awfully low, start from n equals 1. Pauli pairs up. The maximum you can put in an orbital is 2 electrons. Hund's ones rule, if you have a choice, do it 1 at a time, and then if you have to go back, you would pair back up like Pauli said. Okay, so now all these things, these pictures I'm drawing, I'm going to write them as letters, because it takes way too much time to draw pictures, right? And you won't see the pictures quite as often. So the letters look like this. So I'm going to explain everything here. I'm going to give you a second to write down what you need to, but I want to explain what this means. So it's kind of like a code. It's like a secret code only chemists can read. And you are soon going to be in that cool club. Okay, you're going to learn how to read this code. Because instead of drawing pictures, we actually just write it out like we want to. We're going to say, all right, I'm going to talk about hydrogen. How many electrons does hydrogen have? Hydrogen. Electrons. 1. Great, so I'm going to start really easy. Because on the periodic table, a little castle here, hydrogen's up here. So if you remember from last unit where you guys had to kind of outline the periodic table, remember you went through and labeled the rows as the periods, right? So this was period 1, that was for hydrogen and helium, and then row 2 was everything else across. So these are periods now. Period 1, period 2, and so forth down the periodic table, right? So guess what? Period 1, it's called energy level 1. Nothing tricky here. So energy level 1 is noted by a huge coefficient of 1 in the front. So energy level 1 is represented as a coefficient, and that correlates with period or row, don't forget periods or rows, 1 on the PTOE. This is generally a rule, so I'll put a little asterisk down here that because we're gonna have that change just a teeny bit on us later. All right, so energy level 1 you represent as a large 1, and then you get to say hydrogen is really small. It's going to fill that smallest shaped orbital first, which is an s orbital. The s shape was what shape? Circles, a sphere, right? So s is just saying the shape of the orbital that you are working with. What are the 4 shapes or the labels that we put with those shapes? S, P, D, and F, right? S was a sphere, P was a dumbbell, D was 2 dumbbells, and then F was a flower shape. So they get more complex as you go into more electrons. And then you get to tell me how many electrons are held in that orbital. So remember, the maximum you can put is 2. And hydrogen only has one electron to work with, right? So it's not going to have two electrons, it's going to have one electron. So this s orbital is only holding one electron. Another way to represent this is to actually draw the electron, and it would be represented by something called an orbital diagram. So a diagram usually means picture, right? Usually. So a picture in this case is going to be a really crappy picture, but I'm going to draw it anyway. It looks like this. Line, that line means orbital. Which orbital? It's the 1s orbital. How many electrons are in my 1s orbital? 1. Remember, we draw electrons as arrows. So this is the orbital diagram for hydrogen. Orbital diagram is a picture. This is the electron configuration of hydrogen. Electron configurations are like letters and numbers. So do you see there's two different ways to display exactly the same thing. Electron configurations are like 1s1 or 1s2 or 2p6. We're going to see that one in a second. Or you can describe it as an orbital diagram. I think they go great together though, because you should see 1s, 1 electron, and an arrow means 1 electron. All right, so these always are going to add up to the number of electrons that a particular element has. So if I give you something like this, actually let me make up another one. If I go 1s2, I'm in the first row, right? I have an S-shaped period, or a S-shaped orbital. What does this 2 represent? Number of electrons, right? Who has 2 electrons? Helium. So this is the electron configuration for helium. Because I'm saying I have 2 electrons and that's it. How would I write the orbital diagram? It's almost exactly the same. It's dash 1s like that. But what do I put in here? 2 electrons, 1 up and 1 down. Remember, they always spin opposite, because if not, we got a magnetic field going on. All right, let's keep building. Let's go to, I'm going to go further. I'm going to go to oxygen. Go on oxygen. So I'm going to scratch this for a second. Let's go to oxygen. I just need more space, really. Okay. So I want you to give yourself a quick sketch of the periodic table. Make yourself a little castle with a little river on the bottom. Moat. And I want you to make a division here and here. Give yourself a sketch. Okay, if your element that you're looking for lies in this left side, this is called S block. Anything in here is going to have the very last configuration, electron configuration we're talking about, is going to be labeled S. Anything that lands here, like oxygen I'm going to do, this is called P block. It's a block, and everything here, the last thing you're going to write is something P. P6, P4, P3, just representing the number of electrons there. Everything here is D block, and everything here is F block, right. So like I said, the simple ones are spheres, and those are generally kind of upper in this corner. And then we're going to talk about transition metals, which are all D block, and then P blocks over here. So don't forget the 2 towers, they're called the representative elements. So anything in these S and P, they're called the representative elements. That's just a term you should know. All right, so if I wanted to talk about oxygen, oxygen is right here, here. 1, 2, right here. So here's oxygen. So notice that as we go down across the periods, we've changed up the number, the coefficient, which is the period, as we go. So everything in this first row is labeled 1, 1s. And there's another 1 over here. But what S's are here in the P block, right? That's because helium and hydrogen actually belong together. Hydrogen doesn't actually belong in group 1. It's just the only place to put it. So I'm actually going to draw this like this to show you that this is helium. Because helium is a small atom, so it belongs in the simple category of S block, okay? So everything in the first row is period 1, so it's 1s. Everything in the second row is period 2, so this is 2s, and as I go over here, it goes 2p. This is 2p right here. This is 3p, and so forth. As we get here, when we talk about anything in here, we're talking about D block. But as the D block starts at period 1, 2, 3, 4. So I'd notice that when you talk about D block, see how it's subtracted 1 from the period? So it goes 4S and then it goes 3D. Well, we're not in the third period, right? We're in the fourth period. There's this little rule called N-1 for anything in D block. N-1 just means that you take whatever your period number was and you subtract when we start to talk about it. So we're going to do that one in a second. And then when you get down to F block is actually inserts into, you probably saw on your periodic table, it's got like a gap here and here, atlantium and actinium, and it pulls out the whole periodic table down here, and we're going to talk about that in a second. Okay, so let's do oxygen, like I was going to do earlier. What you have to do is you have to count every single electron as it takes to build oxygen. So every electron it takes to build oxygen, you have to go through here, here, and then all the way over here, and then you're going to stop. You're just going in order, chronological order, okay? Or systematic order. So right here you go 1s. How many electrons have I counted for here? 2. 1s2, okay? Now you've dealt with the first energy level. Now we got to go to the second energy level. We're here, so I'm going to write exactly what it says here. 2s. How many electrons am I accounting for here? 2 again. So I'm traveling through these 2, done with the first period. Now through these 2, almost done with the second period. But I got to travel all the way over here, and then I have to start over. I don't start over. You have to kind of just pick up where you left off. Here, it's not S block anymore, but we're still in the second period, right? So then you go, okay, 2p. How many electrons over is oxygen? 4. 1, 2, 3, 4. Okay. So what we've just written is called the electron configuration of oxygen. It's just counting electrons and keeping track of where they exist. And the way I can double check myself is, how many electrons does oxygen have? 8. How do you know that? It's the 8th atomic, it's an atomic number, right? So it's neutral, it's got 8 electrons. How do you check the number of electrons here? Add up the exponents, right? 2 plus 2 plus 4 is 8. Boom, we got 8 electrons, that's oxygen. All right, so that's still the electron configuration. What's up? Got it? Good. Okay. So that's the electron configuration. The orbital diagram is going to be a little different, and I'm going to draw that. See if I can move. I'm going to draw it here. So we just said oxygen was 1s2, 2s2, 2p6. Draw out this orbital diagram with me. 2p4, thank you. 2p4. So the orbital diagram for 1 is just 1s, right? How many electrons go into it? How many? 2, because it says 2 right here. So arrow up and arrow down. I do lazy arrows, I do half arrows. Okay, next one, 2s. How many electrons? 2. Okay, this one's different. P had an up and down orientation, a sideways, and then coming in and out, right? So you actually have to draw a dash for each of the P orbitals, because there was a P x-axis one, a P y-axis one, and P z-axis one. You have to draw all of them. I don't care if you're using all of them, you have to draw all of them, and then give me a little bracket and go, these are all 2p. Because you need to identify those as P block. Okay, now there's 4 electrons here. According to off-ball, we've been doing good. Awfully low, started off at 1, now we're going to 2. Poly, we're still doing good because we're pairing them up. What was Hun's rule again? Right, 1 in each. So I have to fill it up 1 at a time. 1 electron here, then 1 electron here, and then 1 electron here. So how many electrons have I used from P block so far? 3. I got 1 more. I have to go back and fill it up. So if you didn't know Hun's 1's rule, though, you probably would have went 1, 2, 3, 4. That, if you did that, totally wrong. The whole electron configuration would be wrong because you're not following those 3 scientist rules as to how the electrons are best suited for their environments. Okay, so this is called a what? And this is called a orbital diagram. I know it doesn't look like you're drawing anything, but you are. That's a diagram. All right, so who feels good with that? Yeah? All right, we got to work on this more. Let's do another one. Let's do a harder one. Let's go down to silicon. I want to write the electron configuration for silicon, so I want to get all the way here. How many electrons do I need to have in the very end? 14. Okay, so you're going to find that you are redundant because you write down the same thing a lot. So start me off. 1s2 because you're accounting for hydrogen and helium. Helium is actually over here. Okay. Next. 2s2, because you're going to be, I'm going to kind of scratch them out as we go. Hydrogen, helium been taken care of. These two have been taken care of. Next, 2p6, good. Because you're going to go all the way through here. So now we've traveled through here. 3s2 is going to be down to those, 3s2, and then 3p2. Count up your electrons on the exponents up there. 14, yeah. Okay, so we have 14 there. I want you to see something. You'll never forget that 6 electrons is what you can fill up in p block, because one, there's 6 elements here, 6 electrons, right? And how many electrons could I have put in all of these? 6. That's why you have 3 orbitals with 2 electrons each, right? So thinking ahead, if I get to d block, which is down here, how many spaces am I going to have to draw in my orbital diagram? 5, because I have how many electrons to deal with? 10, and there's 2 in each orbital, so 2, 4, 6, 8, 10, right? So let's go further. Let's go down to iron. So I'm going to continue though, okay? Because we've already got the hard work. We got this, over here. Okay, so I'm going to adjust this last one. Instead of saying 3p2, just draw it there again. Instead of saying 3p2, what do you want to write right here? 3p6 is we're going all the way through here. Okay, now I'm down here. What am I going to say? 4s2. And then, what did I say to do when you enter D block? -1. So you don't say 4D, you say 3D. So 3D, 1, 2, 3, 4, 5, 6, right? Iron's the 6th element over. So 3D6. How many electrons should I be counting up there? 26. Yeah, you can't see that. It says 26 right there. Okay, so if I drew this out, I would have to do a 1s, a 2s, with the electrons as noted, 2p6, all of those would be filled, right? Did we have an orbital for the 3s with how many electrons in it? 2 electrons, because we have like this, 2 electrons there. And then what would I draw next? Say again? But what do I draw? 3 orbitals with how many in each? 2 each, because I filled them all up. So I drew those 3 spaces with 2 each. Then I get here and I just draw a single orbital, 4s, and I put my 2 electrons there. And then what do I do when I get here? How do I draw 3d6?
You do 5 orbitals.
Okay, so 1, 2, 3, 4, 5, and all of those are called 3d. Okay, and then what do I do?
Put 1 arrow in each.
Right, one's roll 1, 2, 3, 4, 5, and then do what? 1 in the first one. So at the very end, you have this 3d6 to deal with. You have to draw all 5 orbitals, because there has to be 5 orbitals for this full d block to have 10 total electrons. But there's only 6 spots taken up. So you do 1, 1, 1, like Hun's 1's rule said, and then you go back and refill. Okay, we're going to go over more of this. I don't know why the bells didn't ring. We'll go over more of this tomorrow. Don't worry. Try some of these on your problem set 5 tonight. But if you want to ask me questions, I'm here for school. And if you want just to ask me questions tomorrow, because we're going to be continuing our discussion on this tomorrow, okay? Bring problem set 5 tomorrow, because I want to see all your progress on the EMS spectrum.